We ended by talking briefly. Wednesday, whatever. The exam is next Wednesday. So we talked about on Monday with our cycloalkanes, we started with that. You notice that the formula changes and starts to mimic that of the alkenes. And that's because an alkene is ultimately a two-membered cyclic structure, right, if we want to kind of compare it in that respect. So your cycloalkanes will lose two hydrogens, which means they all have a degree of unsaturation for a single ring. Okay? We also considered a little bit about the energy of each of these structures. Remember, the hybridization in each of these carbons is sp3 hybridized. If we're sp3 hybridized, what bond angle do we get? So sp3 means 109.5 degrees. And this is where we can pull from our geometry classes the bond angles within a triangle, an equilateral triangle. 60 degrees. So we're taking carbon atoms that want to be 109.5, and we're now compressing them down to a 60-degree angle. Okay? That puts a lot of stress within that ring structure, and it wants to pop open. So cyclopropanes tend to be fairly reactive, at least in comparison to some of the other rings. Okay? What happens when we move up to the cyclobutane? What's our bond angle? It's going to have to be 90 in a square. At 90 degrees, again, we're compressing that bond angle down. I would recommend that you at least half-heartedly attempt to build a model for both the cyclopropane and butane. Depending on which kit you've purchased, you might be able to build both of them. If you've purchased the one that I would recommend, which is that Darling model, I'm going to steal yours for a second. It looks like this with a bunch of loose pieces. Do not attempt to make the cyclopropane, okay, unless you are willing to throw away those pieces. Because in the process of forcing that down, you will break it. Okay, that's how much stress there is in that structure. The cyclobutane you can put together, and I would recommend doing that for the cyclobutane for the sole reason that you could then turn the molecule and look at it from the side so that you can't see two bonds, okay, the two parallel bonds on the side. Okay. Why would I recommend you do that? We can see a Newman projection. If you look at the Newman projection for your cyclobutane, what you're going to end up finding out, take a look at a rough sketch of it, is that we're going to have our hydrogens coming off. We'll have that bond in the back, which I'll color blue just so we can see it. What is special about this conformation that I've just drawn? We're in an eclipse conformation. Cyclobutane not only has this ring issue, okay, those bond angles being compressed, but we also get this steric effect from the Newman projection being in an eclipse conformation. So again, our cyclobutanes aren't particularly stable either. Okay? Your textbook will address the cyclobutane does tweak a little bit, and instead of being in a perfectly eclipsed conformation, I think they call it a twist, because it slightly bends off axis, and those hydrogens aren't perfectly in the exact same plane, but it's pretty darn close. Okay? When we move up to the cyclopentane, we're getting a little bit better. I don't know my geometry as well, so hopefully you guys can help me out here. What's the bond angle? Okay, you're as bad as me. I was hoping you were a little bit better. What is it? Oh, we got a calculator. 360 divided by, was it 5?
72.
Roughly 72 degrees. Okay, that seems to be getting smaller. Why is the cyclopentane more stable? 90 is closer than 72. It's not a flat structure. The cyclopentane now has the ability to pucker ever so slightly. And one of those carbons puckers up out of the plane. Okay, comes up out towards us. So if we've got the kit, okay, it's very subtle to see, but if you take a look at the carbon on my left, you'll notice it is not in the exact same plane as the other 4 carbons. Okay? So what's happening is we can alleviate some of that stress of trying to, I'm not going to force it into that angle, alleviate some of that stress on the bonds by puckering an atom out of the plane. Okay? That puckering is what allows for our cyclopentane to actually be more stable than our cyclobutane.
So that increases the space between the carbon atoms, and
That gives us not more space necessarily between them because they're confined by the bond length. It's still all carbon-carbon bonds. What that puckering is going to do is cause the hydrogens that are outside to twist off axis, and you're no longer in an eclipse conformation that you would have gotten with the butanes.
your theta there is 108.
Yeah.
It's
You
not
say it looks larger than 90, there's only 72.
It's smaller than 90. It's broader than 90.
Oh, so it's 108.
That puts us pretty close.
So it's pretty close.
So it's actually getting closer. There we go. So that's better. Okay. Yeah, I don't know my geometry. I'm not going to touch that. Let's just leave that one alone. So what ends up happening is our cyclopentane is now again getting much closer in bond angles and symmetry towards our sp3 hybridization, that 109.5 degree angle. Okay. Is it 108 in cyclopentane or 108? Okay, that's the issue. Okay, 108 in cyclopentane is true. 72 in a cyclohex or a heptene. What's that structure? It's a pentagon. There we go. There's the word. Geometry. Where are you? In a pentagon, you're looking at a 72 degree angle. In cyclopentane, it's 108. Why does that angle open up? It's opening up because of that puckering on the structure. So in our cyclopentane, because that carbon can rotate upwards out of the plane, it allows for a larger spreading of those bond angles. Okay, so it's getting very, very close to the bond angles that we need. Okay, it still doesn't look like 72, but 108 seems a little bit big for that. What happens when we move to the cyclohexane? Okay, we could jump to, oh, it's 120 there? Oh, okay. What's the issue now? Now it's too broad, so now we're causing those bond angles to open up even more. Okay, what is the actual bond angle in cyclohexane? So now not in a hexagon, but in cyclohexane. It matches the sp3 hybridization. Okay. For it to do that, it must again pucker the atoms out of the plane. So when you take a look at a cyclohexane, we definitely don't get a flat structure. Okay, and I've got a couple models here, probably enough per row. You can see that all of our atoms are not in the exact same plane, at least not all of our carbon atoms. That puckering is what's making our cyclohexane exceptionally stable, okay, in comparison to all of the others. When we move up to cycloheptane, so 7 carbons, we have an additional issue popping up with that. Now we're starting to get sterics. Those bonds can freely rotate a lot more. Okay, and because of that, we start to see secondary effects as far as energetics within those structures. Okay, I've got enough roughly for 1 per row, so if I saw model kits already there, I skipped you. Sorry. You don't have to use it, but we will be looking at that in a little bit. Okay? So, what we're now going to go through and do is think about those rotations. Can we ever completely rotate about any of those bonds? After all, it is a sigma bond. Can I do a complete rotation?
No.
Why not?
You can't.
The ring prevents the full rotation. All right, so at least on the sturdier kits, feel free to try and grab one of those carbons and rotate it all the way around. You won't physically be able to do it, okay? At least not in any way, shape, or form that's pretty. Okay? So within a ring structure, we lose rotation. It's interesting. We think back to our cycloalkenes. Could we do rotations there? Cycloalkenes with the double bond, no. We lost that rotation as well. Okay, so our alkenes and our cycloalkanes have very similar properties in that respect. Okay? Really? Yeah, okay. Sorry, I didn't think I was going to talk about that right here. But we are. So we've already talked about different identical structural and stereoisomers. Okay, those relationships, remember that flow chart? We're going to expand that flow chart hopefully later today. But before we quite expand that, what is the relationship between these two structures? So if we go through and we'd start with our molecular formula. Do they have the same molecular formula? Yes. What's the next question we ask? Are they... I already forgot my next question. I don't even know my own flow chart.
Same connectivity or no?
Do they have the same atom connectivity?
Yes.
Or if we got a cyclohexane, do we have carbons attached to the same carbons on the ring? Yeah. We've got carbons located at position 1 and 2. Okay, so we have the same atom connectivity. Are they superimposable? No. If they're non-superimposable, we're now looking at stereoisomers. Okay, and we're going to have to evaluate those in a little bit more detail by branching stereoisomers up into a couple different categories. Okay? When we're looking at our cycloalkanes, we can tweak the naming on these, and we can refer to them as cis and trans. What does cis mean? Cis means they're on the same side. So what we're referencing is that those methyl groups are both wedged. So if we look at the ring as a flat structure, are the methyl groups both on the same side of that ring? Yeah. Our methyls are both on the top side in the case of this drawing. What happens in the trans situation? I don't know why I made that an ethyl group. But they're on opposite sides. Same and opposite get too difficult to manipulate, don't sound sciencey enough, so we come up with cis and trans. So cis means our groups are on the same side of our ring, and then our trans means on opposite sides.
How can they have the same formula?
Oh, yeah. I don't know why I made it ethyl. That was the issue. I'm positive it was methyl initially. There we go. So the relationship between these now is stereoisomers. Otherwise, they were different because they had different formulas.
So
Yeah.
first molecular formula, then atom connectivity, and then whether it's...
Yeah. If anybody, somebody have the flow chart up?
Yeah.
What is the sequence on it?
It goes.
At least the initial one.
It's the same molecular formula.
Molecular formula, superimposable atom connectivity. So superimposable shows up pretty early in that. Okay. Questions? Okay, so this is just introducing the idea of cis versus trans. That's all we're really trying to get at here because it will show up a whole bunch. So I decided to jump strictly to the cyclopentanes and the cyclohexanes and pretty much skipped the propanes and butanes because they're just highly stressed. They aren't as much fun to look at. Okay, so we want to look at things that are lower in energy. If we look at these models, so if we built out the cyclopentane and we tried to draw it, this drawing doesn't accurately reflect that shape. Now remember, whenever we use a solid line, that solid line means that we're saying that though that bond is in the plane of the paper. Okay, wherever we're drawing. So that means, again, if we look at a cyclopentane, what we'd be saying with this drawing is that it is entirely flat. Those carbons are all in the same plane. And when we build that model, you'll notice that it wants to pucker. One of those carbons will pop up out of the plane. Which means if we're going to draw this accurately in 3 dimensions, this doesn't quite reflect it. Okay? A better image would be something along these lines. This is where it becomes difficult because we're trying to draw in 3 dimensions here. Okay. And what we're trying to represent is that that bond is going backwards, so it's behind the plane of our paper, So is this one. This bond out front is coming out at us. And we have this back carbon behind, and then we have our other bond connecting everything up. Okay. By attempting to draw that in 3 dimensions, what we're saying is that these 4 atoms are in the same plane. Okay. That plane in this drawing is actually coming directly out of the paper. Okay. It is perpendicular to the plane of our drawing. This atom is now up out of that plane. Okay, so we're trying to draw perspective without showing perspective. Okay, that is exactly what's happening here. Okay, so it's not the easiest thing to pick up, but you have to become familiar with what these notations represent. Yes? What's that?
From this another thing.
So we're taking our structure. Let's see if I can line it up. What I've got drawn up on the board is what we've got here. Okay, notice the carbon with the green and the red are above the plane of the other 4 atoms. Okay, so that's what this drawing is supposed to represent. Okay, does that make a little bit more sense?
From a viewpoint, though.
In this case, you're looking at it directly as I'm showing it to you. Okay. If we overlapped all the bonds, then all we see from the side is that shape. Well, that's pretty useless to look at. Okay? So we end up, instead of looking at it directly from the side, twist it ever so slightly. Okay? That slight twist allows us to then be able to see all of those individual bonds and atoms so that we can draw them a little bit better. Okay? What does this shape kind of look like?
Lawn chair.
No, it's not a chair yet. Our cyclopentanes, their most stable conformation gets referred to as the envelope. Okay. We've got the 4 corners of our envelope where you would put your letter, and then you've got the flap that folds over the top. So it's typically referred to as the envelope shape. Feel free to go through and play around with the Newman projections on that. I'm not going to test you on those, but you should be able to look and see what happens with the overall alignment of those bonds. And hopefully you'll see that they twist a little bit out of exactly eclipsed. Okay? What happens when we try and do our cyclohexane? Okay, again, if we take that model that you guys have and look at it directly from what I would say is the top of your cyclohexane. So I'm going to grab the closest one. If we look at it from the top, what's that shape look like? Particularly from this distance, it looks like all those carbon atoms are in the same plane and we've got a hexagon. So what we're drawing with that hexagon shape is a representation looking at our structure from the top. What happens if instead of looking at it from the top, you look at it from the side? Okay. If we look at it directly from the side, I know there's a bunch of other atoms on that model. If we look at our cyclohexane directly from the side, what we should see is something along those lines. All right. We've got one atom coming up out of the plane of the other 4, and another atom coming down. Okay. Now if we use our imaginations, what do we have here? We've got a chair. That chair is facing this direction. All right, wait a second. Again, we can't see all of the atoms in this drawing. So what we would want to do is twist our viewpoint on the structure. And instead of looking at it exactly where all the bonds overlap, we twist ever so slightly so that we can see our atoms. Sorry, I'm going to twist it the way I can see it. We can twist it ever so slightly so that we can see all of our atoms. Okay? The reason we want to do that is so that we can better and accurately reflect that 3-dimensional structure and see all of our carbons. When we go through and do that, what we end up seeing, let's see if I can draw this chair. we have our chair ever so slightly twisted. Okay, so that we can now see all 6 carbon atoms. Please feel free to draw this. There will be a quiz later on where I'm going to make you draw it, and you will find that you will suck at it. Okay? That's what happens. As you work at it, though, what you'll end up finding is that you will become really, really good at drawing one of them, the chair facing this direction. If we turn it around to try and make the chair face that direction, you'll find that one will look horrible. Absolutely unintelligibly horrible. Right? You end up drawing one a little bit more frequently than the other, and you just start to draw that one naturally better. Okay? To be able to draw these, it really does require practice. Through Sapling, I believe they've got a little cheat tool for you when they want you to draw chairs, and they'll give you the chair, and then you can say, doop, there's a chair, and you don't have to deal with drawing it all out. Okay? Tim, what was your question?
Will you please label those carbons as either equatorial or axis?
No, for a couple reasons. Number one, we aren't quite there yet. And number two, the carbons are not axial or equatorial. It's the substituents on the ring that are axial and equatorial. Okay? We haven't talked about that term yet. For those of you that weren't in the lab on Monday, that probably means nothing to you unless you read ahead. Okay? We'll talk about that in just a little bit. Okay? So let's deal with drawing these chairs. Okay, this is how I would recommend that you start with this. Okay, and I'm pretty sure, yeah, I did do it this way. Okay, we want to stepwise through this as neatly as possible. And if you really looked at how quickly I drew that last one, I went through these individual steps because it's the only way I've found to consistently draw a reasonable chair. Okay, so let's go through. Reasonable is an opinion, just so you know. Okay? We want to start with the seat of our chair. So we want to draw 2 lines that are staggered and parallel to each other, slightly angled. Okay? So roughly the same length. Okay? You notice they're staggered off of each other. I could go through and angle them the other direction. Okay? We'll talk about why we'd want to do that once we finish all of this. Now what we'll do is pick the left or the right side of the chair. It doesn't really matter. Okay? And we want to identify the short line on that side. So really what I'm saying is if we roughly cut each of these structures in half, okay, roughly through that middle section, okay, and now we look at, let's go for the rightmost structure, and we'll start with the rightmost side of it. Which line is shorter, the one on top or the one on bottom?
Which side of the line?
It's a right-left issue. Let me try that again. Maybe. The rightmost chair is this one here. So we'll call this right. And I want the rightmost side of that chair. Which line is the shortest? Did I say longest?
No, you said shortest, but you didn't specify right side or left side.
Okay. I thought I did that too. Okay.
Right, left, right.
So we'll go far right side. The line that is shortest is where? On the bottom. Because it's on the bottom, we will draw our chair downwards from that point because our line is on the bottom. Once we've got that line, we can then connect it with our other carbon. Okay. Whoops, that should be an orange for completing the triangle. Okay. Let's go to the left side. Okay, our LL side. Which side is shorter, top or bottom? Okay. Thank you for the just kidding. We want to draw downwards again because the bottom line is shorter. Connect. And we've got the bottom part of our chair. Then we can shift to our other side. So now we'll go to our right chair with our left side of that chair. Which line is the shortest, top or bottom? The top, so we'll go up. Whoops. Whoa, go away. I know. I was seeing it. We'll go up because it was the top line. Connect. What do we now have? we've got our chair facing which direction? To the right. That was completely unintentional, but I'm glad that worked out. Our right chair is facing to the right. Okay, I thought it was cooler.
So if you just try to make all that opposite, but like you said in lab, I know this meeting thing, but if you look, you can see the lines that should be parallel.
If we go through and evaluate the rest of our structure, so I just completed my other chair there, which chair do you think I can draw better, left facing or right facing?
Left facing.
I'm hurt deep here. Our left facing looks a little bit better than the right facing. Okay.
Your footrest is a little small on your right.
Yeah,
Are they supposed to be?
for a shorter person. They should, everything should be even.
Is it supposed to always be
Okay.
downward pointing towards the back rest? Or is that just how it works?
So let's go through and evaluate the other components that when we look at this. So first off, opposite lines are parallel. That line is parallel to that line. This line is parallel to this line. The seats are parallel to each other. Okay? Everything, your opposite side should always be parallel. Okay? Always is a loose term. Mine actually didn't look too bad. They actually look like they're relatively parallel on both of them. Okay? Yeah.
How often would we encounter not always? Does that make any sense? Like,
So the not always means you screwed up your drawing.
oh, so it's not like,
Yeah.
so if we draw correctly, then it should be always.
It should always be parallel. Yep.
Okay, there's no exception.
There is no exception. It should always be parallel in your chairs.
Okay.
Okay. Let's go through and label the parts of these things that are your chair. Okay, so I'll take a look at the left one because I drew that one a little bit better. This is where I would put my head. My back sits in that section of my chair. The four atoms that are kind of angled through the middle there, that is where I would put my seat. Oh no, that sounded weird. Okay. And then the last section of our chair, this is where I would rest my feet. We could ultimately say all three of those is where I'm shifting my feet. All right, so when we reference chairs, when we talk about it, particularly with the individual models, you'll hear me ask, where's the back, where's the seat, where's your feet? Because I need to be able to see exactly what you see. Okay, the issue with that, take a chair and slowly start turning it. As you turn it, you'll start to see that you see different chairs. What once used to be where you would sit has become where you would put your head. Okay? And it's not because it's some weird contortionist act, it's because of different visual aspects of what you're looking at. Okay? So until you become comfortable with manipulating these structures in 3 dimensions in your head, it makes a lot of the questions asked when it comes to chairs very difficult to interpret. Okay? This is why the model kits are there. You can play around with the model kits to get that kind of tactile response so you can better manipulate and see these structures. Questions?
I still have the same question.
Yes, what was your saying?
Always going to be like downward towards the back. Like to see how the seat.
Oh, I see what you're saying now.
In both cases, it's like that, but I mean, you could draw it the other way.
You can draw it any which direction. I've just noticed that my chairs look the nicest when they're aimed that direction.
Gotcha.
Yeah, I actually never saw that. That's just how it actually drew out.
Okay.
So in case anybody else is wondering what he's saying, if you take a look at where the seat is aimed, our seat is aimed down towards the back of the chair. Okay, if we take a look at the other chair, our seat is angled downwards towards the back of the chair. You can draw it the other way, it just looks not as nice. Okay, and I know you think these look gorgeous and all, but
It doesn't matter.
it does not matter. As long as you've got the components in here and in the relative shapes, I can figure it out. Okay? So the next part of this, oh man, and I just erased all my chairs. If you take a look at your chairs, I had a red and a green atom on those chairs. And I had them spaced in interesting positions. Okay? They were actually on different carbons. But you should be able to go through and adjust this. If we look at R and G in this case, okay, are those the same? No. That R1 is pointing directly up. Where's the G1 aimed? It's a little bit down-ish is usually the description. It's kind of going horizontal. So our R group is in this up-down axis, and our G group is in the left-to-right axis. So if I went through and drew on another bond, say here and here, which ones are, top or bottom? I know, it's kind of iffy.
Repeat that?
So let's back off here. If I draw on this bond, everybody see the bond that I just drew in? Where is that? Is that R or G? That is R. Let's draw in the other one. R or G? That one is very difficult to see at that position, but it is G.
Yeah, look like straight.
Okay. How can you tell that in the three-dimensional drawing? Or sorry, our drawing? Not very easily. Build the model. In the model, you'll see that that atom that I've got marked as G is coming out of the plane of the structure. It's not on the up-down axis. What happens if I draw in this bond?
That's a R.
That's a G. What's that atom? You guys see a pattern on this?
No, what's that?
Okay. Those of you saying yes are cheating. You guys already had a lab on this. Your R atoms are always in this up-down axis. Okay. And they will point the direction of the triangle. I know, give me a second.
What do you mean?
So we'll use our red. So let's take a look at R1, the first one we looked at. What do I mean by the triangle? There's the triangle. Where is that triangle aimed? Up. Where should the R bond or the R atom be? It needs to be drawn up. So let's get rid of that triangle. Let's take a look at our R2. Again, look at the triangle. Where's that triangle aimed? Up again, which means our R should be drawn directly up. Take a look at R3. Where's our triangle aimed? Largely downwards. Our R group needs to be drawn straight down. What's the G group? How do we draw on our G? Good answer. It's not R. Okay. Officially, your G is parallel to the second bond away. So if we go back, take a look at G1, our second bond away, 1, 2. Here's our second bond. Compare that to the G1 line. They are parallel. Let's take a look at G2. Second bond away, 1, 2. Parallel. What if I counted the other direction? 1, 2. Still parallel. Okay. So if you put together your chair properly with your opposite sides being parallel, every 2 bonds away from any atom is going to be a parallel bond. Okay? So we want to put on our G groups in that not R position. Okay, questions before we bring in new terminology? Yes?
G3, would that be slightly more tilted up because it's the one next to R1?
So if we take a look at G3, looks like I didn't draw G3 quite as nicely. 2 bonds away, 1, 2. It's kind of close. It's not perfect, but it's kind of close to being parallel to that second bond. What if we counted the other direction? 1, 2.
Which one?
You guys go up more.
Yeah, that one's... So when you
question-
draw a bad chair, your parallel issue becomes problematic. Take a look at our two lines. Those aren't parallel at all, and they are on the opposite sides. They should be parallel. So I drew a bad chair. Okay? So this is one of those issues. You have to be careful about how you align those things.
So,
Question.
on your exams, when you're asking us to draw a chair and you ask us to label that or whatever, are you gonna count us off for that?
Parallel, no. But if you go through and tell me that G3, because we haven't talked about the terminology yet, if you tell me G3 is actually an R group, yes, I will absolutely mark you off for that. Okay? So you need to be aware of where those groups are relative to each other and label them appropriately. This R and G thing is something we just made up because we use red and green kind of randomly. What is the R group typically referred to as? It is our axial group. The G group is your equatorial.
Question.
Okay? Yes.
The G group, how can we know that each one pointing up or down?
How do we decide when we're drawing our equatorials, do we draw our line parallel on the upside of the structure or the downside of the structure? So let's take a look at G3, because I think that one's going to be the easiest to evaluate. Okay, you've got a valid point. Why did I decide to draw it? And I'll go through and color it in purple. Why did I draw my parallel line going upwards and not parallel downwards?
Because you have R3 going down and they can't be.
Equatorial, first rule, is not our R, or not our axial. Okay, where is the axial position in that case?
Down.
It's pointing down. It's that R3. So that means the equatorial must be aimed, not R3. It has to be aimed up. So if you drew on G3 and the bond aimed downwards, putting it over there, I would probably understand what you meant, but you would probably lose some points because you drew it in the downward direction, which is what matches the axial position, not the equatorial. Okay? The next issue is this looks like a beast to be able to interpret. How can you see this better? Model kit. Put the model kit together. When you look at the model kit, you will see where the equatorial and axial groups are, and you'll get the idea on why we're drawing them in these particular directions. Because when you look at the model kit from that angle, that's where these bonds are best drawn. Because they best reflect that three-dimensional structure. Who knew this was an art class, right? Okay, so we just evaluated that our R groups are up and down. I like to refer to them in our axis, or on our axis. And our G groups are equatorial, or in kind of the equator, the plane of our cyclohexane structure. Okay. Well, if they're in different positions, do you think that has something to do with their energies? Yes. One of those positions is higher energy than the other. Okay. So if we decided, for instance, that our R groups, our axials, are all in high energy, what they're going to try and do is move to look like our G groups, our equatorial. So how can R1 move to look like a G group? What would it have to do? It's going to have to bend downwards. Okay? At the same time, R2 is going to be doing that. R3 is going to be doing the opposite, moving upwards. What is happening is what's known as a ring flip. That does not mean you take the ring, our nice little chair ring, and flip it over. Okay? What we're referring to, and this really only works for those of you that have it in your hands, is we're going to take our former back, which is what I'm holding with my thumb, and I'm going to turn that into my feet. And I'm going to take my former feet and rotate that up into my back. And what you'll notice is that all of the bonds end up shifting locations. We're rotating about the sigma bonds within the ring. Okay? That rotation was not possible in the cyclobutanes, not possible in the cyclopropanes, and very limited in the cyclopentanes. Okay? What you'll end up finding is as we go through and do that, we can force our R groups to become G groups, and our G groups will necessarily have to become R groups. So we get an alternation between these two. Okay, so when we look at a cyclohexane, it is freely rotating about those single bonds. And we end up converting anything that's axial into the equatorial position and anything that's equatorial into the axial. So we're oscillating back and forth from those two possible conformations. In the case of this chair, in the case of cyclohexane, does it matter which conformation? What are all of the groups in cyclohexane? What are all the substituents on the ring in cyclohexane? Hydrogen. What's the difference between a hydrogen and a hydrogen? Nothing. So there is no difference in conformational energy. What we can end up doing is put in a different atom. Instead of it being hydrogen, let's put on a carbon. If we put on a carbon, we're necessarily putting on a carbon with 3 other hydrogens. We're putting on a methyl. Okay? Where is that methyl going to want to be? In that axial position or in that equatorial position? So what we would have to do is evaluate the energies of that dynamics. How do we identify energies? You have to use Newman projections. Okay? Those of you not in the lab, I will be posting a model activity to Canvas that goes through and asks this very question and forces you to draw the Newman projections for a particular structure and prove that the equatorial position is more stable than the axial. Okay? Those of you in the lab will really love that question because it takes you probably a half an hour to get through and solve with help. Okay? And the end of it is put it in the equatorial position. Okay? So how do we go through and do this? What we're going to do is take a chair conformation, and what we're using with these eyeballs is we are sighting down those bonds. So we're losing, mark that in red, this bond, cannot see it anymore, and we cannot see this bond anymore. Because we're sighting down 2 bonds, we have 2 Newman projections. Those Newman projections are attached to each other because those bonds are part of that ring structure. So if we take a look at our chair, from our top, our overhead, our side for our chair, and our Newman projection is now turned this direction. All right, that kind of aims for everybody on the left, right? You're on the left side of the classroom. Okay. And what ends up happening is we've now lost that back carbon. It disappears from your view, and that's why we have to use the Newman projection to be able to visualize that. Okay. When we look at our cyclohexane as what's shown here, there is no difference. Okay. If I go through and look at my chair, I can take this carbon and flip it upwards, and this carbon and flip it downwards to go through the chair flip. But it still puts hydrogens in all equatorial and axial positions. There's no difference in energy. Okay? So what we want to go through and do is change those groups. Instead of looking at hydrogens, now let's make it something else. What is that something else going to be? It doesn't matter. Okay? As long as it's something other than hydrogen. So in this case, I've got 2 positions marked differently here. One is marked with an E, which stands for equatorial, and the other one is blue, or A, sorry, for axial. Okay? If we take a look at this chair, what's going to end up happening is that axial position is going to freak out. Okay? We already said that our axial is higher in energy than our equatorial, so it's going to start to move up into the equatorial position. And the process of that transition, we're going to end up rotating about a bunch of those bonds and cause a new change in our structure. Okay? So if we do that rotation, we've turned our blue atom into an equatorial position, which was formerly A. That's what the parentheses are for. But as we shift that one up into the equatorial, our old red atom now gets shifted into an axial position as well. We can't keep them both in the equatorial plane. Okay? So between these two, which one's the most stable? It's a kind of a difficult question. Okay? Why is it a difficult question? What's the difference between E and A? We don't know what E is, and we don't know what A is. Okay? If we said A was a hydrogen and E was a methyl, which structure is more stable, left or right? So E is our CH3, and A will make a hydrogen. Which structure is more stable, left or right? Left, because our equatorial is more stable than our axial. So we want that group to be in the equatorial position. Okay, why is it more stable? It's a much harder question. Look at the Newman projections. What we're concerned about is that E, and we're looking at a Newman projection, so we're concerned about its relationship to the other atoms within that Newman projection. There's a hydrogen right there. What type of interaction is between that hydrogen and that E? It's a Gauss interaction. Okay? We're never going to see an eclipsed in this case because they're all staggered. Okay? That Gauss interaction is higher in energy. But are we ever going to eliminate that E-hydrogen interaction?
No.
There is no way to get rid of it. It is always going to be there. Okay? That's why hydrogen is all over the place. So what we want to do instead is look for something other than hydrogen. So comparing to hydrogen is useless. What's our other atom that's attached to that structure? Which carbon? I see two of them. Top or bottom? Yes, the one I want to look at. That is correct. What's the bond angle between these two? What carbon are they attached to? The exact same carbon. If I rotate about a single bond, so let's pull this off. We got hydrogen and carbon. If I rotate about that bond, what happens to the distance between those two atoms? Stays the same. No matter what I do, that interaction is always there. That orange interaction does not help us. Okay, that is atoms connected to the same thing. For a real Newman projection, to see that energy difference, I have to look at the interaction between that atom on a different position. What we're looking at is the relationship between these two groups. What is that Newman projection? We have the anti-alignment. Can't end there. What we'll need to do is go through and take a look at our axial position and see what's happening to our axial. Okay, there's our axial. What are we going to compare it to? Which CH? Again, the bottom one, because those are the ones on opposite carbons or in different carbons. What's the relationship between those two? That is a Gauss interaction. Which one is higher in energy, Gauss or anti? Gauss. Which conformation is more stable, i.e. the lowest energy? The one where we're in an anti-alignment. Okay. When are we in an anti-alignment? Axial or equatorial? Equatorial. Okay. So you've got a whole bunch of different terms floating around on you. You have to make sure you keep track of all of those individual pieces. The questions that you will typically see are referencing which of these conformations is the most stable for X structure. Okay? So you would have to draw out that structure or look at each of the answers and say, oh, that one puts the biggest group in the equatorial position. That one's my most stable.
How do we look at this and decide which one's equatorial and which one's axial?
How do we see equatorial and axial? In the Newman projection, it's a little bit difficult. Because ultimately our equatorial and our axials are coming from our chairs, not from our Newman projections. Where was our axial located? Up or down?
Oh,
Where's our axial position here?
down.
Straight down. Anything in that completely vertical axis is going to be what position? Axial. Where's our equatorial located? Yes, it's up, but is it in that straight up and down vertical axis? No, it's slightly off to the side. We're looking at that atom following through the equator. Okay, that one's equatorial. Okay, we just went through 3 different viewpoints on cycloalkanes. A 2-dimensional overhead view, which if we want to show up and down, we have to use wedges and dashes. Then we have a 3-dimensional chair. Okay? Within that chair, there are several aspects that are implied as far as the 3-dimensional characteristic. We can then further rotate that into the Newman projection. Which of those 3 structures should we use? Depends on the question that's asked. If I ask about energy, which of those 3 projections makes the most sense? Newman. If I ask which one's the axial position, Newman works, but our chair is ultimately where it's coming from.
So much easier to see.
Okay? It depends on opinions, but you're right. Okay? If I ask you to perform a chair flip,
Call it clown.
you have to use the chair. If I'm concerned about the arrangement of the 2 groups, say I put 2 groups on a ring, and I want to know if they're cis or trans, where is it going to be easiest to see that relationship? In the 2-dimensional, where I've got either both wedges or wedged and dashed. I can still see the arrangement of these groups from the Newman projection. I can still see it from the chair. It's just a heck of a lot easier to use the 2-dimensional overview. Okay, along those lines, let's go ahead and erase all of that. What is the relationship between E and A? Are they on the same side or opposite sides of the ring? Where's our axial group aimed? Down. So one thing we'll find is our axial groups are very easy to see. They're either up or they're down. Where's our equatorial group aimed? Diagonal. Okay, so that's a little bit difficult to interpret. Okay, in a 2-dimensional, our ring is all on the same plane. We're either dealing with wedges and dashes for our substituents. So if we aren't comfortable with identifying our equatorial which direction, then let's label the axial. What's the axial position at that carbon? Where is it located? It's the hydrogen aimed downwards. If the hydrogen is down, where does our equatorial atom necessarily have to be in this case? Not down, which is up. So our E group is up. Where is our A group? What's the relationship? Inverse works. What's the term we use? Trans. Go all the way back to our cis-trans arrangements. Okay. Your equatorial groups will absolutely be the most difficult to decide which side of the ring they're on, which is why identify the axial position first. The equatorial will have to be the opposite of that. There is no other option. Okay. We will be doing lots of practice with this in lab, so hopefully you'll get a little bit more confident with it. The biggest lesson to learn from all of this, where do we want our largest group to be located? Put it in the equatorial position. Which position is easier to draw, axial or equatorial? Axial. Okay, so if you want to put it in the equatorial position, but you can't draw it, that makes it very difficult. So how can you make sure in your drawing that I know you mean it's in the equatorial position? Write equatorial on it. Okay? If your drawing's bad, just specify that it's equatorial or it's axial. Okay? That way, even if it's drawn horribly, I at least know that you know what the answer is, and I can give you credit for it. If you give me some vague chair, so we draw a real quick chair. I know I didn't draw that properly. And you draw on, let's say, this bond.
We don't know what you're talking about.
Come on. There it is. Where's that red bond, axial or equatorial? There we go. That was exactly what I was fishing for. Half the class said equatorial and half the class said axial. That's because it is not in a position that we understand. Okay, your axial is straight up and down. Your equatorial is not that direction. Okay, so how could we add information to this to specify one way or the other? We could go through and say, this is E. I now know you mean equatorial. What's the other thing you could do? Now where is it?
No, it has to be equatorial.
Our E has to be equatorial because I've specified my axial position. Okay. The other option is we could go through and do this one. Okay. That's going to be even more confusing to interpret because you've now clearly identified your equatorial position, which would say that other one that looks horrible is the axial. But you're going to put it in such a confusing way to interpret that I probably won't be able to give you any credit for it. Okay? So you now have a couple ways that you can get around drawing horrible chairs. Specify that information and you should be okay. How big of a deal is this for your final exam?
Big deal.
How many chairs do you have to draw on your final exam? Exactly 0. Remember, it's multiple choice. What's your question?
Yeah. Can you explain about the transposition? Basically, trans based on what?
We'll talk about the cis and trans after class. We'll talk to you directly about that. Okay. Let's go ahead and take the first example. Let's take a look at one. I want the lowest energy conformation for cis 1,2-dimethyl cyclohexane. What's the first part of this question actually asking? Provide the structure means we're going to need what? A chair. Okay, because we're looking at our lowest energy conformation. So we're going to have to provide a chair. Okay, so one of the natural tendencies for people to do is immediately draw a chair and say it's dimethyl. So I want my methyl groups to be placed in the equatorial positions. And they're located at position 1 and 2. So here we go. There's an equatorial. There's an equatorial. Just because I want to be nice to whoever's grading this, this one's axial, this one's axial. These are my CH3s. Is this the correct answer? It's wrong. Why is it wrong?
You didn't specify 1 and 2.
Nope.
They're not on the same side.
The first part of this question indirectly asked nomenclature. Okay. You need to know what cis means. Cis means they're on the same side. Let's go through and look at our two methyl groups. It's maybe difficult to interpret where that methyl is located. So let's look at the axial. Where's the axial position located? Down, which means that methyl is up. The other one, again, we've got this issue. It's difficult to interpret our equatorial, so evaluate the axial. Where's the axial aimed? Up, which means our methyl is necessarily aimed. Are they on the same side? No. The first thing you should do before you attempt this type of problem is not draw a chair and throw them into the equatorial positions. The first thing you should do would be draw the easiest structure to interpret, your overhead drawing. And when we look at the overhead drawing, I would first go on and put on my CH3s. Now I have my 1,2-dimethyl cyclohexane. It says cis. I need to make sure, wow, that was a horrible wedge. I need to make sure they're on the same side. What I would personally do now, because I already pre-built a cyclohexane structure with my model kit, is very quickly take off some of the extraneous pieces and put on two groups. Okay, two colored balls. I don't care what colors they are as long as they're on there. And I make sure they're on the exact same side so that when I look at that cyclohexane from the overhead, they are both wedged. Now I will take that cyclohexane and turn it into a chair and draw what I see. Now I can put up my answer.
So one's axial, one's equatorial.
And if we go through to fix this drawing, I'm going to fix the easiest portion of this. One must be axial, one must be equatorial. In this case, the one I drew was where they were both aimed down. Is that wrong?
Yeah. Your drawing shows they're both up.
According to your version.
Remember, there is no up, there is no down. As long as they're on the same side of the ring, I don't care which direction they're aimed. Okay? So approach the problem slowly. The biggest solution to all of these is to draw. Draw structures. If you ask me for help, probably the first thing I'll ask you to do is show me your drawings. I want to see what work you've already put down on paper. When you get to an exam where it's a show your work, okay, and this works for multiple choice as well. If it says show your work, and you go, oh my God, I have no idea how to answer this question. For the love of God, do not leave it blank. Because all you're doing by leaving that question blank is that you are telling me you deserve no points. Write something down. Ideally, make it as close to the answer or whatever information was in the question as possible. Give me some reason to give you points. Okay? Same goes for multiple choice. This one kills me even more. On a multiple choice test, there's very few exams that actually deduct points if you get an answer wrong as opposed to leaving it blank. This is not one of those classes. ACS test is not one of those things. If you don't know an answer on a multiple choice test, guess. Put an answer down. Okay? Odds are you'll get it wrong. I don't care. But there's that small probability that you'll get it right, and you now got free points. Okay? Quite literally free. Okay? So make sure you specify that information. Okay? Never ever leave anything blank on any exam I give you. Okay? Because it really breaks my heart. You may laugh at that, but I end up getting very sad when I see blank pages. Okay? I've seen blank pages before too, yeah.
Multiple pages.
That actually hurts even more. Okay? So, we're going to spend a little bit of time looking at Chapter 5. We're definitely not going to get through all of the slides because there's 12 slides on Chapter 5. And we'll see how far we get into it. Chapter 5 is looking at the concept of chirality. It's then going to expand the understanding of classifications. So when we looked at our structures, we could identify identical, different, stereoisomers, structural isomers. We're going to branch out from our stereoisomers into other things. Once we end up looking at stereoisomers, we're also going to have to introduce the concept of a new nomenclature system. And that's ultimately the R and S nomenclature system. I'm going to guess we aren't going to get into the nomenclature aspect of this. Okay? The very last section of Chapter 5, wherever it shows up in the chapter, I'm not positive, is about optical activity. It's how do you experimentally see that you have different structures. Okay? That for sure is not going to be on this test. I already eliminated that. Okay? So, chiral versus achiral. Okay? All structures have the ability to have a handedness. Okay? Humans have a handedness as well. Think about our left and our right hand. Okay? Our left and our right hand can't do exactly the same thing in all cases. Okay? Yeah, they might, well, even if I tried to slap someone, I could probably slap them a lot harder with my right hand than my left hand. Okay? There's a handedness associated with it. You could try throwing something, throwing an object. Okay? If you're right-handed, you can throw that object a lot better with your right hand than with your left. Okay? So humans have this handedness. It turns out molecules also have a handedness with them. Okay? So we have to understand what is that handedness and where it's coming from. A chiral structure, by definition, is not superimposable on its mirror image. So that means draw the mirror image and see if you can superimpose it. Okay? The classic example is taking your left and your right hand. Okay? They are mirror images of each other. My left hand, that is my left hand. All right. We put a mirror right through the middle. Okay? They are mirror images. Are they superimposable?
No.
Okay, and here's the fun part. Everybody goes like this. Of course they're superimposable. Okay? No, the back of my hand must overlap the back of my other hand. Okay? If I try and align that, they do not superimpose. Okay? Molecules will have a very similar issue. And because you're all super confident with three-dimensional structures now, this whole chiral concept should be really easy to work with when dealing with all these mirror images. Yeah, what's up?
No, I was giving you a thumbs up.
Oh, thumbs up. Yeah. It takes practice. You'll get better at it. Trust me. An achiral molecule is just not chiral. Okay? In that case, what we're saying is it is superimposable on a mirror image. The example that I pulled, I'm not sure where I got these pictures from. The example here would be a chair. Okay? If we took a standard chair and looked at its mirror image, Okay, we could directly superimpose that over it. Okay? Think about really cheap socks. Okay, you have to be cheap because sometimes expensive socks don't work. You take a cheap pair of socks, either one will fit on your feet, okay, on each foot. But if you look at expensive socks with, leg cramp, with feet in them, okay, with toes, what's happening with those toes? Okay, I can't put my right sock on my left foot. Okay, it doesn't line up. It doesn't match. Okay, so we have to be careful with what examples we look at. So you will be expected to kind of think about this chiral issue when working with the sapling assignments. You probably won't expect to see more than one, maybe two questions about objects being chiral in the real world on the test because a hand and a chair or sock aren't organic chemistry. Okay? So you're going to be responsible for structures. Okay? This really came about with this particular drug, okay? Known as thalidomide. Okay? Again, those of you that took the lab may already know some information about it, so don't answer this. Anybody know what thalidomide was used for? Morning sickness. It's an awesome morning sickness drug, first developed somewhere in the 1950s. All right? So they gave out the drug to a bunch of pregnant women. They stopped having morning sickness. Awesome, great. They were all happy. Until however many months later, what happened? They gave birth, and their babies had massive birth defects. Okay? The not politically correct term is flipper babies because they lost a lot of their extremities. They ended up with poorly formed arms or legs because of this particular drug. Okay? Well, they went back to their studies and said, no, something's got to be wrong. And what they ended up finding out was that this molecule is chiral. Okay? That little squiggly line in between there is really saying that that line could either be wedged or dashed. And in the case when they first put this drug out there, this was the structure they put out for it. They said, well, it could be wedged or it could be dashed. We don't really care, it still works. Okay? Well, it turns out one form of it cured morning sickness. What did the other one do? That caused all the mutations. Okay? So this concept of chirality is massively important. We've got virtually an identical structure, okay? But it is treated radically different when it enters the human body. Why might it be treated so radically different in the human body?
Depends on the receptor.
The reaction.
Our bodies are chiral. DNA is chiral. Proteins are chiral. That chirality effectively self-replicates. That's going to change how we grab things. Okay? Think about wearing gloves. Okay? If you tried to put the opposite glove on the other hand, it feels very, very awkward and uncomfortable. Okay? Same thing's happening in the body. It responds to that drug differently. And what ended up happening is that small change in that carbon now prevented that drug from acting the way it was supposed to and ended up interacting slightly differently somewhere else that they hadn't even considered or studied. Okay? So this concept is incredibly important but also incredibly difficult to deal with because ultimately the only difference between those two structures is a wedge versus a dash. Okay? So we have to be able to evaluate and look at these structures. So if we go through and take a look at this pair of molecules up at the upper right-hand corner, do they have the same molecular formula? Yes. Are they superimposable? No. And we could see that if we took, say, that rightmost structure and we flipped it over so that the carbon chain matched. In the process of flipping it over, that chlorine was aimed out at you, but then we flipped the structure over. It's now aimed away, and we would have that dash. So we could superimpose the carbons, but not the chlorine. So they're non-superimposable, which means they're isomers. Do they have the same atom connectivity? Yes. So they're now stereoisomers. Okay? If we looked at the names, we'd give them the same names, which makes this even more difficult, because if we're trying to refer to two different structures, and they have the same name, that's a bit problematic. So what ends up happening is that we can evaluate those structures and look for characteristic signals. What we're trying to find are centers or parts of asymmetry within the molecule. alkenes and cyclic structures give you that asymmetry. Okay? We saw that already with our cycloalkanes. Okay? That asymmetry is known as a geometric isomer. Okay? The other one is looking for these chiral molecules, or a chiral center within the molecule. The biggest tip-off is to look for an atom that has 4 different things bound to it. As long as you have 4 different things, you now have a chiral center. Okay? Chiral carbon, stereogenic center, stereocenter, all those words are ultimately meaning the same thing for us. Okay? The other thing we could look for, which again just kind of depends on your abilities to look at these, is a mirror plane. If there is a mirror plane running through the middle of the structure, that structure has to be achiral. If there is no mirror plane, then it will be chiral. Mirror planes are ridiculously difficult for people to see. Well, I should be fair. They're difficult for me to see. I've never been able to see mirror planes, but some people are exceptionally good at finding those. So if we take a look at these 2 structures, where's the mirror plane? Okay, do we have a mirror plane with our 2 structures in the middle? Take that butane structure, and instead of looking at it from the side, turn it so you're looking at it end on. Yeah, there's a mirror plane running right through the plane of the molecule. If we take a look at our bromine one, why can't we just do a plane through the middle there? How many atoms are attached to that carbon? There's 3 shown, which means there's a 4th, the hydrogen. Is the bromine actually in the plane of the paper? No, it's wedged coming out or dashed going back. There is no mirror plane running through the middle of that structure. Okay? These are some definitions. We will see some of these on the exam. So I want you to be aware of the definitions. But what I'm more concerned about is how you would classify them. So when we get into stereoisomers, what we're going to end up doing is now looking for that chiral atom. If you have a chiral atom, then you want to evaluate if they're mirror images. If they're mirror images, whoops, positive is that way. We have enantiomers. That's the relationship between the structures. If we don't have mirror, or they're not mirror images, then they're known as diastereomers. Okay? Or for the uninitiated disastomers, which is also kind of fun to say too. Okay? If we don't have a chiral atom, for instance, our cycloalkanes and our alkenes, that's where we move into our geometric isomers. Okay? You are expected everything up to this point will show up on the test, so you need to be able to classify these structures. That model activity that those of you in lab are going to be working through right now will get posted to Canvas, and I'll let you know where it's posted so you have access to that. Okay? For those of you not in the lab, so you can get that extra practice. Okay?